Hello biology students, and welcome to video 5 of the cell unit. Today we're going to continue our discussion of cell transport, but more specifically we're just going to look at passive transport, which is one of two types of cell transport, and we're actually only going to look at diffusion, which is a type of passive transport. So as you can see by this definition, passive transport we define as the movement of molecules, so that makes sense, transport the movement of molecules across the membrane without the use of cellular energy. And ATP is the molecule that actually stores energy, so we're not going to burn any ATP, and we're going to be able to move molecules. Now this name makes sense. Passive, you kind of think, without energy, kind of lazy. So this is transport that does not require energy. So I had mentioned that the first type of passive transport, and in fact the only one we're going to look at today, is diffusion. So let's look at a couple definitions. So diffusion is basically the tendency for particles to spread out evenly in an available space. So they're going to move from where there's a high concentration of particles to where there's a low concentration of particles. So this box is supposed to be an arrow pointing right, okay, just so you know. And concentration we define as the amount of substance in a given space. So if I have a lot of particles in a space, that would be a high concentration. And if I have only a few particles in that same space, that would be a lower concentration. So here you can see an example of diffusion. So let's say I had a beaker of water, and I placed one drop of red dye in the very center of that beaker. And you can kind of imagine in that one drop there are actually millions and millions of dye particles. And what would happen is over time, these dye particles would spread out until they were evenly distributed, okay? And they're going to move from an area of high concentration. You can see in the center there's a high concentration of red particles, and on the edge there's only water. So they're moving from a high area of high concentration to an area of low concentration, until eventually they reach what we call equilibrium, when everything is evenly distributed amongst the system. So this can happen across a membrane as well. So you can see, let's pretend this is the cell membrane, and I have one substance on one side. These molecules are going to move across the membrane until eventually they reach equilibrium. I have equal numbers of molecules on each side. And the way this works, you can kind of imagine that all molecules are moving. So at this point right here, all these molecules are bouncing around, and because they're so crowded, because there are so many of them, they're very likely to run into one another. And if they run into one another, they're going to be rocketed or pushed in some direction, and they just might by chance be pushed across the membrane. In this second picture, you can see that I only have a few molecules over here, so they're much less likely to run into one another and be pushed across the membrane. So every once in a while, one of them might go the other direction, but not very many of them are going to go that direction because they're not very likely to hit one another because there aren't that many of them. Whereas on this side, there are a lot of particles. They collide very often, so more often than not, they're moving this way. So you can see that's why we move from high to low concentration, because when you have a high concentration, they're likely to run into one another and move to where there's low concentration. Now, one important thing that students often get confused about, when we reach equilibrium, that does not mean the molecules stop moving, okay? They still continue to move back and forth at equilibrium, but instead, they're just moving back and forth at equal rates. So we say there's no net change because the number of molecules moving left across this membrane is equal to the number of molecules moving right. So down below here, I have a slightly more complicated system where I have green molecules on one side and these purple ones on the other side. The same thing is going to happen. But when we reach equilibrium, there'll be equal numbers of green on both sides and equal numbers of pink on both sides. Okay. So diffusion is this concept we've been talking about, how we have molecules using no energy, because it's passive transport, to move from an area of high concentration to low concentration. So when we say this, when we say they move from high concentration to low concentration, and again, that's what this means over here, and again that box is supposed to be an arrow pointing right, we say they have a net movement down their concentration gradient. Okay, so a concentration gradient you see down here, we just define it's a difference in concentration. So the reason we say they move down the concentration gradient, if I drew a little graph and this was high concentration and this was low over here, you can see to get from high to low, they physically have to go down that gradient. So that's why we say in diffusion, molecules move down the concentration gradient because they move from high concentration to low concentration. Okay. So there are many factors that can speed up or slow down diffusion. So for example, temperature. If I increase my temperature, that's supposed to be an up arrow there, I'm going to increase the speed of my particles, and therefore I will increase the rate of diffusion. If things are moving faster, they're going to collide more often and diffuse more quickly. Similarly, if I lower temperature, I'm going to lower the speed of my particles and slow down diffusion. The second one, if I change the amount of solute, if I have more solute, or what we say a steeper concentration gradient, which basically means I have a bigger difference in the amount of particles on one side than the other. What's going to happen if I have more solute? I'm going to get more collisions, so diffusion is going to happen faster. I'll get more diffusion in one direction. The third factor is surface area of the membrane. So if I have a very large surface area of my membrane, if I have a lot of membrane, I'm going to increase the rate of diffusion because there are more places the molecule could cross. You know, there's more membrane that the molecule could hit and cross. So that would increase diffusion. The fourth one is charge of the solute. So if I have something that's not charged or nonpolar, it's going to pass through the membrane really easily because of the hydrophobic tails of the phospholipids. If I have something charged, even if it hits the membrane, it's not going to be able to go through. So something that's charged would slow down rate of diffusion across the membrane. And finally is size. Something that's very, very small can cross through the membrane easier, so the smaller it is, the faster diffusion will occur. Where if it's something a little bit bigger, it will diffuse more slowly because even if it hits the membrane, it might not diffuse through. So that's diffusion. So in the next video, we'll visit osmosis, which is the next type of passive transport.